Okay, so whenever we do a calculation involving torque, the main rule is if you want angular acceleration to be zero, you want angular velocity to remain either constant at zero or constant at something, then there has to be no net torque on the object. The torques going clockwise have to equal the torques going counterclockwise. Otherwise, you will get a rotation inevitably around the pivot point. These gentlemen have done this kind of interesting method for accessing an air conditioner. You see that there is a pivot point for the board that they are standing on. He has a certain mass. The force of gravity on him produces a, let's see, that's clockwise rotation about the pivot point, and his weight is being countered by some additional torques placed on the board from the weight of these gentlemen downward, which I'm going to write as if it were one thing. So that weight provides a force downward at this distance, r. So Fg times r is the torque in that direction. And rather than saying clockwise and counterclockwise, I always just write an arrow because it's easier than remembering what clocks do. It's the digital era. Anyhow, on this side, we have the weight of these two gentlemen put together times, and since I'm taking them together, I'm going to go to the center between them, times this distance, r. I'm going to call that r1, call that r2, and the torque in now this direction, because this force tends to rotate the board in this direction, the torque in that direction is equal to Fg on the two men times that second distance we're talking about. If this man's weight times his distance happen to be larger than the sum of these two men's weight times their distance, then there would be a net torque in one direction or the other. The board would rotate. Of course, I'll note that there's also, this is not simply a balance on this pivot point. The board, due to the normal force coming from the shelf, is not really free to rotate in that direction. So these men are in no danger of overbalancing this fellow who's working on his air conditioner. I don't recommend this approach, physics or not. Okay, so when we talk about torque, we have a number of applications that we can think about. Presumably you've all at some point changed a tire or seen a tire changed by someone else. Wheel is held onto the axle arrangement by a set of lug nuts, which, needless to say, are attached to the car quite tightly because, well, you don't like it when the wheels come off the car while you're driving. Turning the lug nut to untighten them requires quite a bit of torque. Generally, you can't apply that torque easily yourself. So we use a lug wrench, and I'm going to, let me draw it this way so I have it out of the way. We use a lug wrench to provide that torque and multiply the effect of the force that I or you can manage to put on that wrench by giving a much longer handle, a larger distance from the object that needs to rotate about its axis. Again, the rotational axis here is going into the piece of paper. You can probably apply this idea also to all sorts of things like, opening jars, things like that. I want to think about a pair of scissors, though, because nobody really thinks about scissors as a torque example. Here's a piece of paper. Actually, I'm at home. I have a pair of scissors right here. Here are my scissors. There we go. Here's my piece of paper. For a piece of paper and a fairly good pair of scissors, I will expect to have no trouble cutting the paper even as I've positioned the scissors. If I turn around and take something a little tougher, something that looks like junk, so I can probably do this, and place the scissors with, yeah, I can angle this with the camera, place the scissors so that it's pretty far out, I can squeeze and squeeze and find that I have trouble cutting that piece of paper. Of course you say, hey, I went to preschool, unlike you, I graduated from preschool, and you might explain to me that because you learned how to use scissors in preschool, you know that what you should in fact do is place the piece of cardboard or whatever right up close into the jaws of the scissors, in which point you can cut it readily. So here are my scissors. I want to actually consider this pair of scissors this way. Let me draw them. Here's the pivot point on the scissors. Here's one jaw of the scissors. Here's the other jaw of the scissors. Here's the piece of paper as well. Actually, I probably should have drawn it up for clarity. Here's the piece of paper. The condition for cutting the piece of paper is for the jaws of the scissors to be able to rotate together. I'm taking this jaw as stationary, and I want to say that in order to cut the paper, I need to be able to rotate this jaw towards that jaw. Alternately, I need to be able to rotate this handle towards that handle, but that seems a little far from my piece of paper. My piece of paper, if it does not want to be cut, and yes, I really am personifying a piece of paper here, if my piece of paper doesn't want to be cut, then it needs to provide a torque that counteracts the closing force of this pair of scissors. Did that make sense? Let's stop and think about that for a second. We're used to thinking about scissors. Now I'd like you to think from the piece of paper's point of view. The piece of paper does not want to be cut. The piece of paper, in order not to be cut, needs to be able to prevent the jaws of the scissors from closing upon it. In order to do that, the piece of paper needs to be able to provide a torque sufficient to counter the closing torque provided by my hands on the handle of the scissors. So let's consider first the piece of paper, now the blue one I'm drawing in here. Here it is. Here it is out here. This is the situation I have here, where I've gripped my piece of paper very far out into the nose of the scissors. I don't know why that's the nose and that's the jaw. It's very strange biology. But anyways, so piece of paper needs to exert a force upward on this jaw, which is attempting to rotate, as I said, downward towards the piece of paper. The piece of paper is, well, paper. It only can exert so much of a force. But it's exerting that force at this distance r from the pivot point. R is big, so as a result, the torque here is big. And perhaps it's big enough that I can't manage to provide enough torque to close these jaws together. that being the case here, where I can put quite a bit of force on this and I can't seem to get it to cut. Now let's consider my situation here. Here's my piece of paper, which has been correctly, as we were all taught in preschool, snugged up into the jaw of the scissors, right up near the pivot point. It's able to provide back that same force, but now the torque for that location is equal to the force times a much smaller distance from the pivot point. Here's R here. In that case, the torque itself that the paper can put back on the jaws of the scissors to prevent them from closing, that is a small torque. Okay, and now you understand how to operate a pair of scissors. I guess your college degree is worth it. Let's talk briefly about wheels. Here you are at a bowling alley. You throw the ball, essentially. I know the bowling alley doesn't like that, but you do it in a way that it doesn't like cause one of those dings to the wood. You throw the ball down the alley. When the ball hits the wood of the alley, it attempts to slide. Picture yourself throwing a square ball. You'll understand that the square ball's motion will be to slide, and the square ball, yeah, I really did just say square ball, but picture what I mean. The square ball will slide along the alley for a certain distance, its velocity dropping from its initial velocity due to a friction force which is decelerating the square ball. We don't bowl with square balls, for probably a good reason, which is this. The ball wants to slide in this direction. That's the direction of motion that it's attempting. When the ball attempts a motion, a sliding motion, when anything attempts a sliding motion in the real world, then a friction force arises to counter that attempted slide. We know how to calculate the friction force. I'm going to just leave it as F sub F here, but just notice that F sub F, so the friction force, is providing a force occurring on a round object at some distance, the radius of the ball, from the center of mass of the ball. When that happens, it provides a torque on the ball, causing a rotation in that direction. And in fact, go bowling this weekend, you'll find that the ball will rotate in the expected direction down the alley. As you are rolling, you have a new surface continually coming into contact with the bowling alley and then pulling instantaneously right back out of contact. You have no sliding motion actually happening during the rolling of the ball. As a result, there is no sliding friction acting on the ball. When a ball gets to sit on a surface for some more extended period of time, more than the instant that it's in contact at any one point as it rolls, but let's say it's just sitting there, then there do arise forces between the molecules of the ball and the molecules of the surface that provides sort of an interleaving effect. So that instant of getting the ball rolling requires breaking that interleaving. We call that static friction. the friction that's associated with something not moving. As soon as the ball gets into motion, however, as soon as these surfaces are taken out of contact, then there is no opportunity during the ball's rolling for surfaces to interleave in any significant way. And as a result, there is no additional static friction that arises once the ball is in motion. That's why it's called static friction, stationary. There's also no sliding motion, because any attempt to slide the ball results, in fact, in a torque that provides a rotational motion that is constantly bringing a fresh surface of the ball in contact with, frankly, a fresh surface of the alley as it progresses down the alley. As a result, the rolling of a ball, or the rolling of a wheel, is effectively frictionless. Of course, if you're talking about a wheel, you do have friction at the point of the axle and so forth. You do have, for a real wheel, and a ball for that matter, a deformation effect, which means that as molecules deform as it rolls, think of a tire deforming under a car. It's a little more sort of macroscopic. During that deformation, the flexing of molecules within the material itself has a frictional component, or something, a component like friction, which causes heating and causes loss of energy. But standard friction as we know it when something is sliding does not apply to a rolling ball.